So She256 is, as you all know, an awesome organization, and really happy that they allowed me to partner with them for this peer circle. So I'm one of the mentors for this group, and basically I have developed a program called Bloom, which is a blockchain, Web3, and crypto development program for technical women and genderqueer people. So my kind of mission right now is to get more gender diversity into the Web3 ecosystem. That's something that's really important to me, in particular because I entered the ecosystem because I saw people who looked like me. And I really don't think I would, be here and be a developer in the space if that hadn't happened. So a little bit of context on that. I was living in San Francisco in 2017, lived there for a year, and I started to get to know the SF cryptocurrency dev group. It was a meetup group that would meet like twice a month-ish, and a little bit more. And if for people who were around the space in 2017 or have heard about it, it was one of like the major kind of hype cycles, bull markets that we had. And yeah, so everyone was talking about crypto basically. And as I was getting to know people in the city and going to events, it was just like, incessant, like people talking about Bitcoin. And so that's how I basically started learning about it. But in particular, the SF cryptocurrency dev group, it was run by people of color, and also just always had a very diverse set of people in attendance. And that really contributed to my ability to learn. So I'm basically creating Bloom so that I can kind of cultivate an environment where people who are typically underrepresented in tech can also have a positive learning experience. I've also done like a few other programs that you've probably heard of. So like Gitcoin kernel, which is amazing, highly recommend that. I've done the Consensus Developer Bootcamp and a few other things as well, just learning in the space. So yeah, okay, I will stop talking about myself now. As we start, I think it's good to like level set, like how did we get to where we are now, where we have like DeFi, we have these smart contracts, right? We have all these protocols, layer 1, layer 2, proof of stake. How did we get here? And so I'm kind of going to make this like interactive and really just like create it as I go. I like to start by explaining, just what Web 2 is in a very simple diagram. Okay, so I have these 3 nodes, and they're really, really large, and they're called Facebook. This one's called Amazon, and this one is called Google. Okay, so like pretty much the internet is these 3 players today. And like that doesn't really come as a surprise, I think, to most of us. But what it means is that, all of our interactions online, all of our like exchange of value, the way we communicate, the way we like create information about ourselves, all of that is kind of like controlled within these 3 nodes. And so I like to call this like the Bermuda Triangle that we all exist in. And so the data like that we have on the internet today kind of lives in the Bermuda Triangle. And it just kind of goes into the void in a way, right? Because once that data gets created and uploaded, we don't really know what's happening with it. We know to some degree on the user level what's happening, but beyond that, like it's very opaque. So it's very hard to like understand how our data is being used. And of course, like the past 5-ish, 10 years have illuminated a lot of problems with that. Data privacy, people like taking advantage of social media platforms, right? Manipulating elections, manipulating people's preferences, radicalizing people, all of that, right, is happening because we have these major players that control and in some ways, some people might say, I would believe, exploit the data that lives inside of these ecosystems. So Web 2, right, is like this kind of data silo. And there's like a lot of good benefits about having a network, a very large network with a few players, because it means you can like control and scale very easily, right? You can control the information flows in a very efficient way. And then you can scale the services very easily because you have a few set of ways to coordinate. So there's a lot of advantages to that. But of course, like there's disadvantages too. Someone wrote in the chat, some folks consider these FANG companies. Yeah, I like the word FANG too. Some folks include Microsoft, and basically everyone is centralized. Maybe minus Apple, which is a bit more transparent about privacy than Facebook and Google. Yeah, I would say that maybe minus Apple, but at the same time, it's kind of hard to leave them out. In particular, because they control the hardware, and so we have a centralization of the hardware in use as well. But yeah, very good points there. It's not just these three, like literally, but overwhelmingly, it's a small set of people. True, hardware monopoly, exactly. So then, okay, so then we have Web 2. And so now, like, what does that mean that Web 3 is? So Web 3 is like completely different. It's a completely different topology, right? Where in Web 2, you have like a few really large nodes. In Web 3, you have tons of really small nodes. And it's debatable, since this is a pretty technical group. I'm sure you know that it's like a little bit debatable how small these nodes actually are and how many of them there actually are. But in theory, right, what Web3 looks like in the near future is this like very large, just like massive organization of nodes that essentially have equal ability to participate in the network. And again, there's like a lot of asterisks here. There's like a lot of caveats here, but really like on the protocol layer and kind of foundationally, these nodes in this network have equal chances of participating and having transparency into what is happening in the network. So that's like a huge paradigm shift. And I'm sure, again, like that you all know this, but it's like really important to like reinforce how like great of a difference this is. So any of our computers can participate in these networks to some degree, right? Like we could validate information that's going on the Bitcoin blockchain. We could validate things that are going on Ethereum. You can use like a Raspberry Pi, right? A small computer to participate in these networks. And that's because like the protocols, one, are open source. So there's a lot of trust. There's the ability to actually verify what's going on. And two, like they're super lightweight and like they're designed to be that way. They're designed for this accessibility. So in this diagram, I'm just showing, Bitcoin, Ethereum, and these kind of like data stores. The pink one being just a general database, and then the blue being an IPFS node, essentially. And so I'm not going to like go too deeply into these different protocols here, but like the basic idea is that you have a few different protocols that everyone can participate in. And so that's what makes up this decentralized peer-to-peer network. Okay, and so when we think about like Web3 like abstractly, we also can't avoid talking about the origins of Web3 and cypherpunks. So it's not just like we have this straight arrow from Web 2 to Web 3. Like in the middle of that, we have tons of things going on politically. We have tons of things going on socially and in the internet with engineers who are building these things, and in mathematics with cryptography. And so like another point that I really like to hit on here is just the power of cryptography, because like this network, this topology is not really possible at all without cryptography. Like we need a way to be able to verify without a doubt within a common language what information and activity is happening within the network. And crypto is that common language that we use. Okay, yeah. So I'm gonna show this link to a paper. So this paper is the B-Money paper by Wei Dai. You may or may not have seen this, but it is one of the few works that's cited in the Bitcoin paper. And you can like, I mean, I'm not going to go through this entire thing. It's very short, so you can read this, very quickly. But like the first sentence, right? I'm fascinated by Tim May's crypto anarchy, right? And again, this is like one of the few papers that Bitcoin actually references. So it's the origins of cypherpunks and crypto anarchy are like necessarily tied to the origins of Bitcoin, and therefore like necessarily tied to all the things that we have today that have spawned from that. So yeah, like just what are the cypherpunks and what is crypto anarchy? It's a few names here of cryptographers or people who have been in the cypherpunk movement. David Shum is a popular one that you might recognize for his contributions to like digital cash and Bitcoin and the other forms of digital cash that we have today, but mostly through the form of like cryptography. We have Tim May, who is like one of the early people in Bitcoin, obviously Satoshi Nakamoto. I don't know every one of these people, but these are names that you're going to recognize. Julian Assange, you might recognize too. So anyway, like this group of people make up cypherpunks, right? And they essentially believe that cryptography is a way to kind of unlock individual freedoms for people. I'm not going to say that they all have the same aims and the same exact motivation for the work that they do, but kind of playing in this space of saying like, we can actually use cryptography in ways that allow us to eliminate some of these existing structures which are not operating in the best interest of people at large. And so a really good example of that, which I like to talk about, is Tim Jenkin. Okay, so again, I'm not going to like read through all this, but want to share the link with you. So Tim Jenkin, he was basically just a student during the time of the apartheid in South Africa, and he was a part of the anti-apartheid movement. For the work that he was doing, he was basically like passing out flyers, trying to spread information about the movement of the African National Congress, I think it's called. And he was arrested and sent to prison. And then he like got out of prison by basically creating wooden keys for every door in the prison. There's like a really good movie where what's the guy who's Harry Potter? I can't remember his name. But anyway, the Harry Potter person is also Tim Jenkin in this film. It's a really good film about the prison break. So that's like kind of one of the claim to fame, I guess, that he has. But I think more importantly is the work that he did to actually help to end apartheid. And he worked very closely with the ANC, as I mentioned, and Nelson Mandela to do this. And he was coming from a background of a very logical and analytical person. And that was kind of the way that he was able to provide value to the movement. So there are a lot of people in the ANC who were tasked with organizing individuals, right? They were tasked with like communicating with different people, keeping them motivated, spreading awareness, all of these things. But they ended up having this difficulty of not actually having reliable forms of communication. And so Tim Jenkin, as a part of the party, basically saw this happening and tried to come up with solutions. How can we communicate better, right? And so this is like late 80s, early 90s. And essentially, to cut the long story short, what he was able to do was come up with a way to encrypt messages. So he taught himself how to code on these like very early computers, right? And then he translated the written message to an encrypted audio signal that they then played through telephones, through public telephones. So then one person would play it right into the telephone as they were on the line with another person. The other person would record it. They would then go back to their computer and translate it and be able to decrypt the message. So he came up with this, cryptographic scheme that allowed people to have a very reliable, yet like private, completely private way of communicating. And that was critical for the ANC and allowed them as an organization to help Nelson Mandela get out of prison at the time. And so that's just like one kind of example of the power of cryptography. Obviously, if you didn't have a way to encrypt these messages, like you wouldn't be able to have a private conversation. The phones would be monitored, right? And then the plans would fall apart entirely. So a really good example of cryptography at work and the power of it. And around the early 90s is the same time that we saw kind of the cypherpunk organization being formalized, right? So like the name cypherpunk being coined and kind of some of their values being solidified around the same time. Cool, so we talked about cypherpunks. I did talk about ANC. And so now kind of like coming back to modern day, right? We have cryptography, we have the cypherpunk movement, we know the power of cryptography. And we know the power also of like decentralized systems and these like kind of peer-to-peer networks. But really the problem comes down to incentives. So in the Tim Jenkin anti-apartheid example, right, they have a very strong incentive because they have something they believe in, and they have, the ability to bring their brains together and come up with solutions. And they're very driven, like they're not going to stop on this mission. When we when we take a step back and think about just like the internet at large, we don't really have the same incentives for most of the services, right? Like we prefer convenience mostly, and that's changing a little bit these days because of all these like news scandals and things like that. But like mostly we prefer convenience to other things like privacy and all of that. And so what that means is like it becomes hard to maintain a decentralized peer-to-peer network because people are not really incentivized to do that, or they're not incentivized to overcome the challenges or even like invest in developing the technology so that we can overcome those challenges. And this really changes with the introduction of Bitcoin. So 2008, we have the Bitcoin paper released. And now you have a peer-to-peer system that has incentive mechanisms built into it. And that's not something that we see even in most of our peer-to-peer systems today. The incentive mechanisms are not necessarily built into the protocol. There's other incentives for people to use them. So like HTTPS is a good example of a protocol where like we are incentivized to use it because it ensures that we're not downloading malicious things from the internet, right? We can verify the signatures of the content that's coming into our web browser. There's an incentive to do that, but there's also like centralized entities that exist to ensure that HTTPS works, right? And they're certificate authorities. So they are the people who kind of make sure that once you get that certificate, it's coming from the correct person and it's valid. So HTTPS is like, I mean, it's a universal protocol, but it's only P2P to a certain degree. And so, I'm sure like the Ethereum ENS, like the Ethereum name system, we have like Handshake now, which are trying to actually come up with like truly peer-to-peer and decentralized ways to do something similar, which is like resolving domain names. But it's difficult to do that when you don't have built-in incentives into the system. And so with a blockchain, like we have the ability to do this now because you can earn rewards for participating in the security of the system, right? You can earn rewards for ensuring that it stays decentralized and uses the cryptographic primitives that are going to be the most valuable. So at this point, I think it's good to just dive a little bit deeper into how do we build a incentivized, decentralized system. And so I'm just gonna go through like what a blockchain actually looks like. You've probably seen diagrams like this before, but I think it's helpful to kind of dive into some of the details. So we have some people here who have computer science backgrounds, so you'll be familiar with a linked list. So a linked list is, essentially a data structure where you have some information in something that's kind of like a block. And then you also have pointers to previous blocks. So we're going to actually go right to left instead of left to right here. And so this is our Genesis block. And then this is our, block 1, block 2, block 3. It goes on forever, pretty much. So we have the Genesis block, and then once we create another block, it points back to the Genesis, right? And another one points back to 1. And so this is just a linked list. What makes it kind of different, and one of the things that makes it different in a blockchain is that we're using crypto. So instead of just having, plain data in here, plain pointers in some encoding that you would have in like, any programming language, Java, for example, all of these get represented as hashes, right? So we take a hash of the information that exists in that block, and then we use that to point to that block from the next one. So block 1 has the hash of the Genesis block. Block 2 has the hash of block 1. So just to demonstrate, in case people haven't seen kind of what hashing looks like, I'll pull up my terminal. So I just did this like earlier. So this is using a tool called OpenSSL, which is very common on most machines, I'm pretty sure. And it allows you to kind of create like hashes, use cryptographic schemes to create hashes. So one like important distinction here too is when we talk about cryptography, it's not all about encryption. So like we have encryption as one thing, and then we have other kind of schemes that we use which are not related to encryption. So encryption is about using a key to basically hide something from someone else. Hashing is not really hiding something, but it's actually the mechanism that you use for verification. So in this example, I just typed the word Genesis. I used OpenSSL to get a digest using the SHA-256 algorithm. And this is the hash that it produces. And so basically inside of this block, I would have this long hash, which is a pointer to the previous block. And then just to demonstrate, I could switch this out with another scheme. I think I can do MD5, and then I generate a different type of hash. And then of course, I can put in anything that I want. So say hello, everyone, right? And now I get a new hash. And so what we have is a scheme that's deterministic. And so what that means is every time I hash say hello, I'm going to get the same exact output. And the hashing algorithm that we use has different properties. They all have different properties. And one of those properties is the length of the hash. So you can see like the SHA-256 is longer than the MD5. And then if I do the SHA-256 on this one, so this is the SHA-256 hash of that same string. Yeah, so that's kind of the basics of like, how we would use hashing, some of the basic properties of it, how it gets included in the blockchain. But I guess like one kind of important property of hashing is trying to avoid collisions. So we have this notion of something being what's called collision resistant. And collision resistance basically means our ability to prevent two different strings from resulting in the same hash. So because we have a fixed size of our output, that necessarily means that the set of outputs that we can have is constrained. We can only have so many, but we can have an infinite set of inputs. And so there, in any like hashing algorithm that you use, like you're going to at some point find a collision. The point at which you find a collision is dependent on the hashing algorithm and dependent on the length. So hashing algorithms that result in a longer length are going to be much more collision resistant than ones that have a shorter length, because you're, with a longer length, you're increasing the set of possible characters that can be in that hash, right? And so that means you increase the collision resistance there. So let's say like you had a hashing algorithm that only gave you like 3 characters, right? A, B, C. You can only have so many combinations of that. And so that means you're definitely going to come up with collisions when you're generating that hash. A collision is really bad in most of the protocols, most of the way that most of the protocols are designed. We really don't want that to happen. However, it's not the end of the world. And also it's extremely unlikely that, like astronomically unlikely that we will actually end up with a collision in most of the algorithms that we use today, at least. Okay, so that's hashing, and that's kind of like the basic of blockchain. So yeah, I'll do this one first. Is it feasible to go back from a hash to the word that was encrypted? Okay, so yeah, good distinction. So the hash is not encryption. Those are 2 different things. So that's the first thing. But the second thing is no. So with hash algorithms, they're designed so that you can't actually go backwards. So when I type something in here for my hash, let's just go back to something simple. Actually, it's getting noisy. Okay, so when I type something in here, right, I cannot like take this string and then go back and get Genesis. And that's because math basically is the short answer. I'm not a mathematician. it involves like elliptic curve cryptography and large prime numbers and things that I don't really know how they work, but I know the names of. But it's basically impossible to get from this back to the original string. And so that's also like a really important property of hashing as well. Is it possible for two different string values to have a collision? So yeah, that is possible, but it's extremely unlikely because of how many characters you're putting into the hashing algorithm and how it's designed.
But if that's possible, then it's not a good hashing algorithm, right?
Yeah, exactly. Like I mean, it really depends on the algorithm for sure. But like cryptographers, what they do like every year or just like constantly is like try to break hashing algorithms, right? Like because in their work of designing good ones, they have to figure out if they can break it. And so they're just constantly trying to break these. So there are some algorithms that have been broken, that are known to have been broken. And so like, every few years, we kind of update the hashing algorithm that we use. We make it more difficult because as computers get more advanced, it gets easier for the computers to break these algorithms and to find collisions. So cryptographers are just constantly like trying to come up with like more and more difficult algorithms that really don't produce collisions. And again, like, if you could run a computer through the end of the universe in time, you would get a collision in any algorithm, right? Because you just need more time to do it. But because again, that like there's so many characters in here, it's like not going to happen in our lifetime. There's a little bit of asterisks because it's debatable. When you have very sophisticated quantum computing is supposed to break all of the hashing algorithms that we use today. So there are a set of algorithms as well that are quantum resistant. But yeah, like for now, for all intents and purposes, it's a safe way for us to use services and protocols online. Cool. Okay. So also, if anyone notices that I'm saying something incorrectly, you can definitely let me know. I'm not an expert on this. I've been in the space for a bit, but I'm definitely not an expert. So let me know if I'm messing something up. Can you talk about the distinctions between hashing and multisigs? Yeah, for sure. So yeah, a signature is different than a hash also. So with a signature, what we're doing is we're using what's called asymmetric cryptography. So I'll actually put this down here. So for signatures, we have asymmetric crypto text. Symmetric. And with asymmetric crypto, what we have is two keys. Let's do a diamond for a key. So we have a public key, and then we have linked to that a private key. Okay. And so with these, we use an elliptic curve, again, a math thing, in order to derive these keys. And it's actually, this arrow is backwards. So it goes, we derive the private key, and from that, we get the public key. And so we use these keys to generate signatures. So we can essentially use our private key to sign some message. So I'll do this for here is the message. And from here, we can I put text in here? Yeah, sign. So we use the private key, we sign a message, and then from here, we get this output, which is essentially like a message digest. And so we now like have, actually, this is more accurately, it's a signature. So we now have like a signature that represents, this key signed this message. And the signature that we get is not something that has to be private, right? So the signature can be public. The private key for sure has to be private. Can I change the color? Okay, so gray means you have to keep this private. The signature can be public though. And so once we generate that signature, we now have a way using the public key to verify who signed it. So we don't need to share the private key, but we can share the public key, and someone else can inspect both the public key and the signature. And from that, they can say, okay, I know that, a given person signed this message and they used a certain private key without needing to know like what that private key is. So that's basically how you create a signature. And then with a multi-signature, essentially what we do is have multiple keys signed. That's a very like great simplification. There's different ways that you can do like multi-sig schemes, but it's pretty much just like we're going to have two different people and they're going to generate a single signature. So I'll just add this as like public key A. This will be public key B. And they both are going to sign this message. So the private key is kind of implied here. Put this here. Put that there. Right. And then here is the message for both people. And then again, we just produce a signature from here. So they both sign the message and generate a single signature. And then from there, we can again verify like, okay, this multi-sig was signed by multiple people. So I'll just say, so that it's clear private key signed. So that's the multi-sig. So it's different than hashing. It's using different like cryptographic schemes. I know it's hard to explain a little bit, but I'm trying to like break it down and also like, you know, helps me to remember all the details. So yeah, so with hashing, we're basically taking some input, we're producing this output that has a fixed length. And then with a signature, we're using asymmetric cryptography, using our private keys to sign something. And then we produce that signature that we can verify. So in both cases, like we have the property of verification, which is essential for our blockchain. It's a good example of hashing where we can't go back from signature to public key to private key. Yeah, exactly. So we can't like actually derive, yeah, the private key from the public key. Cool. Okay. And so I guess there's like one other property of blockchains that I wanted to talk about because this is something that you'll come across a lot. Again, if you have a CS or similar background, you've probably heard of a directed acyclic graph. So that's a mouthful. So let's type that out. Directed acyclic graph. And this is commonly referred to as a DAG. And probably as you're reading stuff in the space, you'll hear a lot about DAGs, just like that term being thrown around all over the place. And that's because it's just like an extremely useful data structure. It's like, it makes things very efficient. So kind of briefly to go through what a DAG is, a graph, right, is just kind of some elements that have pointers to each other. They have relationships with each other. Okay, so this is a very simple graph, right? You have one element in the middle, let's call it root. And then you have an A and a B. Zoom in a little bit. So the root points to A and B. A and B don't know about each other. They don't know that each other exist in this graph, but the root knows about both of them. And this is a directed graph because it has little pointy things in the graph. So in an A, I think it's A directed or undirected. I don't remember. But if you didn't have those little pointy things, you would have a graph that's not directed. I think it's A directed. If someone remembers that term, you can put it in the chat. And then the acyclic nature means that we don't have a cycle in the graph. So if we had a graph that, let's say, went like this, and went to C, and then C pointed to the root, this would be a cycle because you can get from one part of the graph and back to it, tracing through this route. So this creates a cycle. If we don't have any cycles, we have an acyclic graph. Okay, so that's kind of like the basic data structure. So how does this relate to blockchains? Essentially, all of the transactions that happen on the blockchain get put into a structure that looks like this. So this is going to be a transaction that says Alex, let's do Alex, sent $5 to Beth. And this is going to be a transaction that says Beth sent $10 to Charlie. Okay. very simplified again, but essentially like we have transactions that get put into this structure. And so what we actually do to create this acyclic graph is, again, we use hashing. So now I'm going to pull this out. Let's see if I can achieve this. Did I do this right? No. Okay. I'll do it like this. I'll put the transactions here. So the kind of top of the DAG is usually what we refer to as the root. And then the very bottom is what we call the leaves. So it's like an upside down tree. So I'll put the leaves at the bottom here. So the leaves could represent, right, our transactions. And we could have like a set of transactions that would make up like multiple leaves. So I'll add one more over here. Like, let's move this little thing here. Let's say that Danielle sent $1 to. Okay. And so now what I've done is I've created like a subtree. So I have this kind of larger tree and I have this subtree. And where hashing comes in is basically in order to create the kind of key, we call it a key, but you can just think of it as a value that represents this part of our graph. We use a hashing algorithm. So we essentially, let's convert this to A5B. And we'll convert this to D1J. And what we'll do to generate the pointer that gets represented here is we'll use our SHA-256 hash, and we'll just hash both of these things, both of these values. A5B, and we'll hash this one. Okay, and so the result of this, which is going to be, quite a few characters, is going to be what lives at this part of our graph. Is this what is called a Merkle tree? Yes, this is what a Merkle tree is called, exactly. So what makes it a Merkle tree is Ralph Merkle invented it. But basically, Ralph Merkle was like, oh, let's take a tree and use hashes as the keys for the different parts of the tree. And so that is exactly what a Merkle tree is. And so, this would be hashing the value. This would like be as. And so now what we have is at each of these kind of subtree levels, we have hashes instead of like human readable data. And what this again allows us to do is verify the information that's in the tree. So what we could do is we can ignore the right half of the tree entirely. Well, we can ignore most of the right half of the tree, I guess. And then we could just say, okay, with these two pieces of information, I can then get this part of the tree. And the only thing that I need to construct the root is the other two pieces. So let's call this, for simplicity, let's say this results in X and this results in Y. So now I can take the hash of X and Y, and that's how I construct the root of my tree. So basically, I can kind of ignore this transaction. Like, I don't really need to know that this transaction existed, because I can, in order to verify these other transactions. So if I want to just say like, okay, did Alex send money to someone? Someone can give me this information about Alex's transaction and give me this information about this other one. They can give me this, and this hash. So I don't even know about any of the transactions that were used to construct this hash. And I don't need to, because I only care about Alex sending money to someone. And so basically what this means is that, as you can imagine, this could get really large, right? Like we could have tons and tons of different types of transactions on this side. And what this means is that I can like cut out all of this data. I can pretty much ignore it to verify a single event that happened. All I need is the hashes that were produced from these transactions, but I don't need the actual raw data. And so this kind of structure makes things extremely efficient. Can you explain how HD wallets work, how exchanges manage people's accounts individually? I can on a high level. I can't in that much detail without some reference. But basically an HD wallet is what's called a hierarchical deterministic wallet. And so essentially what that means is like you have one kind of seed. So with an HD wallet, I'll just put another section in here. I won't diagram the whole thing, but it's helpful to write it out. Hierarchical, deterministic, and we are running up on time, but if people can stay, I'll just do like another 5 minutes. And so with an HD wallet, basically you get some, what we call a seed. So you get some seed phrase or passphrase. It's called a few different things, but in most common cases, you'll see it being like 12 words. So it will be like dog, like machine, robot, happy, Peter. No, there's usually not names actually. Family, cup. So we have a dictionary of some words that are kind of generally accepted in a certain scheme. And you'll have those words, you'll have a combination of those words that'll be kind of used as the input of your wallet. And then from there, you can actually generate a few different types of private keys and private public key pairs. So you'll have, let's do pub key, and private key. So from this, I can generate, quite a few of these things, and they're all going to be different. I'll color code them so that you can see they're different. Red, green. Oh, sorry if someone is colorblind. I probably chose bad colors. But anyway, so yeah, you would have a few different keys, or actually, I don't know if it's an infinite set of keys. It potentially
It's like
is.
2 billion, I guess.
Sorry, say that again.
It's 2 billion around 2 billion account.
Around 2 billion. Okay, yeah. So a lot of keys that you can derive from a single seed. And since we're pretty much out of time, and that was pretty much most of the things I wanted to talk about, I guess I'll just spend the last few minutes talking a little bit about Bloom. So as a part of doing this peer circle, I wanted to offer for anyone who is interested joining the Bloom program. So again, it's a blockchain development program that we're organizing starting in August. So August 14th is the start date. It's a 5-week program. So if you are a woman, if you identify as genderqueer, you're eligible to be a part of it. And then you can just go to bloom.festival.io. You'll have all the information about the program here. And then of course, feel free to reach out to me again on Twitter. So this is me on Twitter. Or on Discord. You can ping me anytime. And that's pretty much all I had. Thank you everyone for being here. Are there any more questions? Okay, general question. If blockchain is decentralized, is there no record of user data stored in a database anywhere? Only servers that do these computations? Okay, that's a great question. Yeah, so I didn't really get into the topology of the decentralized network, but I guess this is kind of a good way to visualize it. So essentially think of these these pink things, these pink database looking things as nodes in the network. So full nodes in Bitcoin, for example, they talk to each other, share information between each other, and store copies of that information. They create these DAG structures, Merkle DAGs, right? And then they create the blockchains and then publish those blocks to each other. So that's kind of how they're always taking in information, they're transforming it, verifying it. And so that's kind of the job of a full node. So when it comes to user data or any data that gets put into a peer-to-peer network, like Bitcoin, like Ethereum, like IPFS, any of the nodes who are connected to the network can have access to that data. And so it's really important to think carefully about what information you're putting on chain, because it's public by default. Anyone can read it. You can also encrypt information before you put it on chain if you want to hide things. But beyond that, any information that goes on chain can be read by anyone. And so, you wouldn't want to put like personal things about yourself. And so in addition to like the computation that nodes do, which is mostly gathering the data and verifying it and generating these hashes in Bitcoin. And then Ethereum on top of that, it's like doing the execution for smart contracts, right? But in addition to that, they also store the actual data because they necessarily have to in order to verify it. Any other questions?
Hey, Wim, can you talk about more about a program, like what we can get and how it will be useful for us?
Yeah, sure. So yeah, Bloom, it's a blockchain development program. So it really is designed to go deep into the technicals of how Bitcoin works, how Ethereum works, Solidity smart contracts, and peer-to-peer protocols, mainly IPFS. So this is kind of, I tried to give like an overview of some of the things that we would dive into, but not all of them. I would say that mostly it's going to be highly technical. So looking in detail at like what the data structures involved are, how you use them, building a naive implementation of a blockchain, things like that. So really, it's designed to like kind of give you the foundational skills that you would need in order to work in the space. And the things that companies would be wanting you to have as you're applying for different roles. So what is the main difference between Bloom and the Gitcoin kernel? So yeah, again, like Gitcoin kernel is a little bit more like choose your own adventure and kind of high level. Bloom has made like two major differences. So the first one is it's specifically designed for women and genderqueer folks. So cultivating a different environment than any other blockchain program that exists. And the second is it's really it's structured so that you're learning specific concrete things. So with kernel, like you can decide what areas that you want to explore, and kind of to what extent you can go do like a more kind of abstract like philosophy type track. You could go more into solidity type things. But there's not like a structured curriculum in the same way. It's kind of just like do it yourself. With Bloom, basically every weekend during the program, we'll be on a call, not a Zoom call, but a similar shared space. And we'll be like going through material together as a group. So that's kind of the major difference between like how the program operates, I guess. I guess another thing to point out is that Bloom has a program fee. And so currently, like we have sponsors that help provide like financial support for people who need it for the program. And then we also partner with companies who are actively hiring. And so those companies, they provide sponsorship funds so that the program can run and people can participate. And then we also allow you to like connect directly with those companies. So you can have one-on-one conversations with them and kind of have an easier way to get to see if you would be a good fit for them.
So it's a paid program, right?
Yeah, yep, it is. Yeah. So yeah, on the website, there's a lot of information here. I'm also happy to share the curriculum out with people. Oh yeah, okay. So let me just share out the link right now. So this will give you kind of the overview of what the program is like a little bit more in depth. And then lastly, as a part of the peer circle, we're offering a 30% discount to anyone from the She256 community who wants to be involved in Bloom. So definitely, since I said that now, make sure that if you do apply, you let us know that, hey, I was a part of the peer circle group and I'd like to use the discount, and we'll send you a discount code for it. Do you know any current Web3 projects which are great? Yes, one of my favorite Web3 projects right now is called Radical.
It's like GitHub, right?
Yes, exactly. It's a peer-to-peer, it's basically a peer-to-peer GitHub. And it's one of my favorite projects because I think that's like a really important thing to have. One, I'm a strong believer in open source. But two, like I think it's very powerful to be able to have a decentralized version of where we host our code. Hosting everything on GitHub is not really the best in the long term. And Radical, they have a DAO as well. They're very transparent about their team, the work they're doing, the roadmap. So I definitely would recommend just checking out Radical. Better than GitLab. So I mean, it's still early. It's still an early project. So like they don't have all the features, you know, that you would expect from GitHub or GitLab. But they've done a good job with what they do have currently. So I'm expecting good things. Cool. All right. I think that's pretty much it. So I think in Luma, it said this was going to 9 p.m. Well, 9 p.m. my time, but that would be 90 minutes. But it was actually supposed to be 1 hour. But I'm glad that I was able to like answer everyone's questions. If you have more questions, feel free to let me know. And it was really great being with you. Thank you for the questions you did ask. This was a lot of fun. And I look forward to staying in touch with all of you. All right, see ya.